Hey everyone, in this AP Chem series video, we'll talk about gas mixtures and partial pressure. First, remember that gases are made of particles with very weak attractions between them, which allows them to expand, compress, and exert a force as they move and collide with the walls of a container known as gas pressure. We also typically assume that gas particles are ideal, which means they have no attractive forces and take up no volume, so their properties can be predicted by PV equals nRT. More importantly for this video in particular is the fact that as those gas particles collide with a given surface, they exert a pressure against that surface. In this video, we're going to take a closer look at what happens when multiple gases are mixed together in the same container. So when talking about gas mixtures, it's first important to know that you can mix different gas particles together in any proportion whatsoever. And because they don't attract to each other anyway, those particles will evenly distribute throughout the container, like the red particles and blue particles shown here. You can also look at the pressure exerted by just one type of gas in the mixture, which is going to be independent of the pressure exerted by the other components. For example, in this mixture, we could look at only the collisions of the blue particles with the inside walls, and therefore look at only the force caused by the blue particles colliding. We'd be considering a value known as the partial pressure of blue particles, written with a capital P just like any pressure, but a subscript that indicates the type of gas you're looking at. If we did the same thing with the red particles, we'd be looking at the partial pressure of red particles in the mixture. If you took all the partial pressures of the gases in a mixture and added them together, it would equal the total pressure of the gas mixture. This is an equation known as Dalton's law of partial pressure. Here, we could get the total pressure by simply adding the partial pressure of red plus the partial pressure of blue. Written more generally, the equation typically looks like this, where the A, the B, and the C represent any gases in the mixture, and the ... reminds us that I could keep adding partial pressures for as many gases are in the mixture. This is one of the key ideas for the video. Make sure you take some time and write it down. Let's also take some time and talk about comparing one partial pressure to the next. In a gas mixture, each different gas is technically under the same volume and temperature conditions as the others. Since each gas has the same V or volume and the same T or temperature, according to the ideal gas law, that means the partial pressure of each gas is only going to be based on one thing, and that would be the quantity symbolized with a lowercase n, otherwise known as moles, otherwise known as the number of particles in the sample. Here's how you could apply this information. Let's say that each of these dots represents an entire mole of particles. This means that the 5 red dots means there's 5 moles of red particles and 27 moles of blue particles. This tells me that there's more blue particles in the sample, which tells me that the partial pressure of blue is greater than the partial pressure of red. Let's get even more specific. What about if I knew the total pressure in the sample already? In this case, let's say that it's 25 atmospheres. From that, we could also calculate the exact partial pressure of each gas using something known as the fraction or mole fraction of each gas in the sample. This mole fraction value is symbolized with a capital X, but it's really nothing fancy. It's exactly that. It's the fraction of red particles in the sample found by counting the red particles and dividing it by the total number of particles. In this case, there's 5 reds divided by 32 total particles, making the fraction of red particles in the sample 0.156. I can then find the partial pressure caused by just the red particles by multiplying that same fraction by my total pressure. So in this case, I'd be multiplying 25 atms, the total pressure, by the fraction that the red particles make up, 0.156, and this is going to give me the partial pressure of red particles, which ends up being 3.9 atmospheres. Let's do the same thing, but calculate the partial pressure of blue particles as well. First, I need the fraction of blue particles in the sample, which is 0.844. Notice it's higher because there's more blue particles than reds. Finishing it off, we'll multiply the total pressure again, 25, this time by the 0.844, ending up with a final answer of 21.1 atmospheres. That will be the partial pressure of blue particles. Let's wrap it up by looking at that equation one more time. PA equals P total times XA, where PA is the partial pressure of the gas in the mixture, and the XA is the mole fraction of that gas, one of our final key ideas for this video. And that wraps it up for gas mixtures. Thanks a lot for watching, and here's a brief summary.